setup. Okay, so this one is going to be dealing with chapter 13, and the title of this is Digital Landscaping, which I know a lot of you guys are already dealing with this kind of stuff, so it's actually just kind of a good overview again. Like I think a lot of this stuff is just overview, but there are some good topics in here, some interesting, I think, that will give you a little bit more insight. It's not going to be specific to any type of software, but just talking about the concept of 3D modeling essentially is what he's really referring to as digital landscaping. So we're going to look at representing terrain, the different methodologies, and some of the types of files that are out there, which some of you might find interesting because you can grab some of these files and use them for limited purposes of not so much engineering, but at least you could look at, like if you were looking at a site in another state and you didn't want to drive down there, this would be a good way of getting some of the information before you send a crew out and that kind of stuff. So it's kind of cool from that standpoint. Then we're looking at some of the ways of representing terrain, quite a few different types of ways, and he does cover that. We do cover that a little bit in here. And of course, a lot of the softwares pretty much have this capability. All your GIS software has that, as well as our engineering software, such as Civil 3D, MicroStation, those kind of things. They all have that pretty much. Look at what a DEM is, which we've talked a little bit about, digital elevation model. And then how you can utilize DTMs, digital terrain models, in day-to-day use. Again, this is not stuff that you guys are not familiar with, I'm sure, but again, it's just stuff to kind of think about. So when we talk about this concept, you know, we think about maps, paper maps, and imagery. We've been looking at primarily, or thinking about that from a two-dimensional location standpoint. So if we want to look at things any different way, then we're going to need to add that 3 dimensions. So it is possible, of course, with modern software to model and analyze terrain features using these geospatial tools that give you that 3D capability. So, you know, prior to this, some of you guys are younger, that you never had an appreciation of not dealing with this, but I know a lot of the guys, some of you guys are probably have, where you didn't have this capability. And, you know, when I was first out there working, you know, everything was pretty much a paper map, and everything that you were dealing with from a 3-dimensional standpoint, you had to visualize or cut it into views to be able to do it. The software just wasn't there at that point yet. And so when I started seeing this stuff come in, I mean, it was just like, I was so used to having to deal with this 2-dimensionally in different views that it sure changed my world. Of course, now, like I said, a lot of you guys never experienced all of that. But it really does make a difference, all of these geospatial tools that we have nowadays. And so whether you're going to be modeling topographic data for different purposes, whether it's construction or recreation or whatever, it's important to be able to analyze this, and these geospatial tools are going to allow us to analyze that really rapidly. And again, all that stuff was, you can't appreciate what I'm saying if you've never dealt with just strictly 2D world, because that was a whole different ballgame. But it actually did, I will have to say this, that it did build skills in me, that when I was able to get into 3D modeling and using the software that we use, I was able to adapt to it really rapidly and have a great understanding of it because of where I came from on that. So this is an example of a map that's showing you the capability of something that Google Earth could do, actually. And what we're looking at is, this is actually a model of Mount Everest. So you may or may not be aware of the fact that all of your Google images like this, they have a digital terrain model underneath them that you can actually download and utilize. So you can take that digital terrain model and use it in, like, say, Civil 3D. What we're looking at is the digital terrain model with what's called a drape image on top of it. So you're actually looking at basically a photograph that has been draped on top of this. So your digital terrain model would be like your framework underneath. So if you strip that image away, it would just look like a normal 10, which is what it actually is. So again, this is just in normal everyday Google Earth software. It's pretty crazy. So when we're looking at 3D modeling of any kind, and you want to examine landforms, you have to have location of the points X, Y, but then we also have to have the inclusion of elevation, which we would think of as a Z value. So each point now has to have that point of a Z assigned to it. So we're looking at X, Y, and Z locations, or it could be northing, easting elevation, or you might think in latitude, longitude, and elevation, those kind of things. But we're actually primarily focusing in on that Z concept. So of course we understand this, like we're all surveyors, so we understand the concept of elevation probably better than most people. But elevations, as we know, are measured relative to some datum. And in this case, we think of that as a vertical datum. We spent time talking about that in chapter 2 quite a bit. And of course, we know that some of those things are changing. But a datum, of course, is just a reference surface, if you will, or a baseline that you can measure elevations above or below. And we normally think that our vertical datum reference is 0, and anything above that is positive elevation. And if you were below that, you would have negative elevation. Now, areas that do experience negative elevation, a lot of times they may have a local datum so that they are not dealing with negative numbers from an elevation standpoint. But for probably the majority of the lower 48 states, we're looking at just straight orthometric height, but you do have areas that do go below sea level, such as New Orleans, and then there's some places like Death Valley, which is really actually negative 200 something, I believe. So of course we know, we talked about this, the current datums that we've had, you know, so the National Geodetic Datum of 29, the NGVD, that's a dead system, but was actually still used by certain branches of the feds. I think FEMA was actually using it not too long ago still. And then this is the newer one that superseded that, and we've talked about all of that. And of course, we have the new one that's coming out, 2022. So that's going to change things again. So a common way of representing three-dimensional view was through a 2D map called a topographic map. And again, we had just sheets and sheets and sheets of these in our office when I was out there working, because we use these readily. And the primary source of that would have been the USGS. But this is a map, that two-dimensional map that shows landscape terrain, and it also shows features of the land. So it's primarily giving you an XY location, but it also shows you through the tool of what they call contours, the concept of elevation. And the primary source of this would have been the, does somebody have a question? Okay, I guess not. So the primary source of this would have been the U.S. Geological Survey, the USGS, and these maps.
Table in the kitchen.
These maps that were produced have been produced for a long time, but they were some of the best that were actually ever out there. And unfortunately, they don't produce them like they used to, but these were great working tools. And so they published a lot of variety of maps, and now most of the stuff that we've talked about before has been on digital. But their primary tool was the 7.5 minute series quadrangle that was a 1 to 24,000 scale. So these maps, the 7.5 minute refers to 7.5 minutes of latitude by 7.5 minutes of longitude. And they're not, if you've ever seen these things, they're quite big sheets, but they're not exact rectangles because of where you are in respect to the relation of the Earth. So the more you go north, the more elongated they kind of get. And the scale 1 to 24,000, that's a natural scale. So that correlates with a scale of 1 inch is equal to 2,000 feet. So this is a really pretty small scale map. And they also distributed them in smaller scales even. And the other scale that was commonly used, which was called a 15-minute quadrangle, and that was at a 1 to 50,000 scale. So not too many people use those, but a lot of people use the 24,000 scale. and they're not certainly great for doing any engineering work, but they were certainly good for just doing exploratory work. So we would use them routinely. Then the USGS has also basically rasterized all these maps, so they've scanned them in, and so it's probably pretty hard to even get those paper maps anymore. I'm sure you can still buy them. You used to go to every courthouse, had the whole series of maps in the county where they were, but I don't even know if they sell those anymore. But now you have the digital format, what they call the digital raster graphic maps. So these are just scan views. So these are called DRGs. They're scanned versions of your topographic maps.
Yeah, they were showing you could buy those online.
What's that, Ben?
You can actually purchase them, and you can purchase all the historical ones from.
Yeah, I think, I know you can. It used to be so convenient because you used to be able to just go
right.
To the courthouses, and I don't even know if they sell them anymore. So, but they are. I know if you guys, we had when I
would not say that's convenient.
What's that?
So I would not say that's convenient.
Yeah, well, yeah. But when I was working, we just had like flat files full of these things, and like so we had pretty much every one that we used within the county. So digital obviously is the way to go nowadays. But these were nice maps to have at one time. So DRGs are available in what's called a GeoTIFF file format. So TIFF is a type of graphics language we've talked about, and so they'll also. The geo concept tells you that they carry spatial referencing data. And the reason that's important is that they're registered so that you can bring these guys in different quadrangles and they'll register up together, they'll match up together. So these are geo references, what that's referring to in that fact, okay? So that's pretty important because if you had, that was another thing in the old days, you'd take these two maps and you'd tape them together on their edges, and then roads on the one wouldn't register up with roads on the other because just they were created differently. So these things are all referenced up now. So topographic maps and also the DRGs contain additional information associated with the map. Now in GIS, we call that data, about data or metadata. So basically you have a border on your paper map and actually on your DRGs as well. It's called a collar, and that collar has all of your information. So it'll include things such as your scale factors, dates of creation and or typically revisions, because most of these maps were done back in the 20s and the 30s and 40s, and so they've just kind of photo revised them over time. And the projection, which is also important in all of these. And other things like maybe true north and magnetic north information, all that kind of stuff is on there as well. So again, it's kind of like metadata or data that pertains to the actual map itself. So this is an example of a paper map. Now, this could also be a digital map as well, but this is what it would look like essentially. If you looked at the piece of paper, obviously, you're seeing the collar on the side here, and we're just looking at a little corner of it. You notice at the bottom, the name of it says Gate City, Virginia. That's called the quadrangle name. So each USGS map has a name associated with it. It's primarily some prominent feature that's usually about in the center of the map. And you can notice the date there that it was originally created in 1938 and photo revised in 68 and 78. And you'll see, if you see purple information on here, that purple information is the photo revised information. So for instance, if you notice that roadway running through there in that valley, you will see that there's actually a purple line there. That's a photo revision that occurred. Now we're not seeing the scale information. I don't think I see that, but that's usually right in the middle. Actually, I can just start to see it on the side. But you do notice there's also coordinate information at the corners. At the lower right corner there, you'll see the 36, 37, 30, and the 82, 30, and those are your latitude and longitudes of that corner. So as you go up from that 36 is increasing, and as you go left, that 82 is increasing because that's your latitude. You also see other coordinate systems on there, which are kind of cool. That's 65 east there, if you see that, that's I think a UTM grid tick. And then the other one over there, it looks like it's in feet. That would be a state plane coordinate grid tick. And then the other one, you got 3230. So that's telling you are at 82 degrees, 32 minutes, and 30 seconds of longitude at that point. So there was a whole lot of information on these maps. And again, that's all associated with that collar kind of stuff. Okay, so let's look at how terrain can be represented. So the traditional 2D paper map to generate terrain use the concept of contour lines. And of course, we still use those readily in engineering purposes, But that's an imaginary line that's drawn on the map. So we don't see contours out in the field realistically, but it's a line of, you guys know, that connects points of equal elevation. So another name for that type of line is what they call an iso line. Iso meaning equal measure. So in a map that portrays just strictly contours is very often referred to as an isopleth. So you'll see other types of isopleths that represent other things than elevation. So for instance, like pressure maps or temperature map ranges, those are also isopleths because those contours could represent changes in temperature or changes in pressure. But when we're talking about land, we're talking about what we call a contour line. And elevations then on that surface are going to be represented by numerous contour lines. And of course, the number of contour lines is going to be dependent on how intense the topography is or how flat it is. So you can have areas where it's very, very flat. You may only have 1 or 2 contour lines running through the entire map. But then you get into areas where it's much more hilly. You're going to have just a multitude of lines. And the distance between any 2 lines vertically that you really can't see, those would be coming at you, is known as your contour interval. So that's the smallest distance that those lines are going to mean in their change. So we'll see that here in a second. But the selection of that contour interval is dependent on typically 2 things, the scale of the map, but also the terrain itself. So you kind of got to look at both. That comes into play. This is an example of that same map essentially, but it's just a little bit blown up. I think this was that same map. I think it was in Virginia. So you notice it's a very hilly area. And what we're seeing is very, very dense contours along here because you're looking at the hills right in the middle, right where it says Creek Knob. That's a hillside. But if you look at the top of it where it's real white, you see a lot of rounded islands or groups of contours. That's probably an area where strip mining's been going on, to be honest with you, if you look at that, because that's kind of at the top of that mountain right there. And that's probably an area where they've been doing that. But our contours here, you have 2 kind of contours primarily. I'm sure you guys are familiar with that. As you look at those contour lines, some of them are darker brown and some of them are lighter browns. The darker browns are usually called your major contours. The lighter browns are your minor contours. And if they have numbers inserted in them, such as 1800 or 1900, that's what's called an index contour. And the typical way, I'm sure most of you guys know this, but if you want to determine what the interval is here between these between contour lines, you look at your two major contours. So if I have 1800 and then 1900, the difference between that is 100 feet. And then I count the spaces between all the contours. So there's 4 contour lines between, but there's 5 spaces. So if you took 100 feet divided by 5 spaces, that would tell you each contour line at that point then represents 20 feet of change. So that's kind of how we do that. Of course, the beauty, this isn't fixed paper, so you can't change your interval. But if you guys know things about like Civil 3D or those things, I can express my contours at any interval I want very readily. So I can make a 2-foot interval or a 1-foot interval or even a 1/2-foot interval just by basically flipping a switch. So that just has revolutionized how things work. So in general, we know that wider contour interval is going to be selected for mountainous or hilly terrain. So what we're saying is we're not going to show as many contours. So instead of using a 5-foot contour interval, we might be using a 25 or even 100. Because if we use too small of an interval, you're just going to see a sea of ink. You're not going to get any data out of it. And if you're in a flatter area, okay, you're going to use a narrower contour. So you might use a 1-foot contour. You may even use a 1/2-foot contour if it's very flat. probably won't see too many maps like that. But with that, we have very few changes in elevation based on that. So scale also is usually a dependent kind of thing. So small scale maps, they're going to tend to use a wider interval because they cover larger geographic areas, but they'll tend to show less detail. So again, if we go to a small interval in that, you're going to have a lot of contours, and it gets to just be too overwhelming. Large scale maps then tend to use a narrower, okay? And large scale maps cover smaller geographic area, but much more detail. So we've talked about all of that before. DRGs are frequently used then for other sources. So you could use them for other geospatial applications, such as in GISs. So if you wanted to get quick information into your GIS, you could take these guys in and use that in there. Then they also have, this is also another product that the USGS has. It's called the US Topo Series. And so this is also digital topographic maps that have been created by the USGS. These also have multiple layers of data. And I think these are a little bit, they're basically similar to those DRGs. But I think they're a little different and probably not just, well, they're probably still the scan versions, but I think they've been cleaned up. But these are in a different format called a GeoPDF. So that's your typical PDF format, your portable file format that a lot of people use. And you can download the geo aspect for that, but what that'll do is then bring in the referencing information for that as well. So these guys have primarily 3 levels of data: contours, hydrography, and boundaries. So hydrography would be things like your river courses, lakes, streams, ocean edge. Contour courses, your elevation, and boundaries would be things like potentially, cities and state lines, those kind of things as well. You can also get transportation features as well as transportation naming. And they also include orthophoto images. So remember orthophotos, we talked about those too, but those are photographs where the relief displacement has been brought out of those. Those have been fixed into a pure photograph that the scale is pure across it so that you can scale things within it. So you can download all of this stuff. I think it's pretty much free from the USGS. This is an example of one of those types of maps. This is from 2013. This is an area of Youngstown, Ohio, and it shows you the available layers that we have for this map system. And this is a good example also. It does show you the collar down here pretty readily, and you can see that information at the bottom. You can see the scale very nicely portrayed. Also, they show you that they're showing you magnetic north and true north and those differences there. There's other information that we can't read, which would be other information pertaining to the metadata piece of that map. So terrain features can be represented by more than just contours. So contours are pretty much just relegated to just flat plane maps, or even if you are working in 3 dimensions, like you might be in using, say, Civil 3D software, your published information for your engineers or your projects or whatever, they're going to show contours as well. But we can actually then model things in 3D. So if we have a 3D model of a landscape, that's very often referred to as a DTM, or we call that a digital terrain model. Now, your author just says basically in GIS, but we know that GIS is not the only software that uses this exclusively. This type of digital terrain modeling is done in all of our engineering software as well. In fact, we've been utilizing it for a pretty long time. Although I do remember the time when DTMs were like brand new, and we were able to just do that in some of the software that we had, and that was it was just kind of an incredible thing once you were able to do that. Because prior to that, again, I don't know, I'm dating myself, but we had to do a lot of that by hand. So where we would go out and generate a grid of points, and then we would interpolate all the contours through any map that we ever did. That was a big deal. So this is not a big deal anymore. But by taking digital information, we can represent that terrain surface by measuring elevations at selected points. And we can do that in one of several formats. A lot of times people use grids. or you can use what's called a controlling point method. And grids, obviously, a lot of you guys have done this out in the field know that just a gridded site where you're taking it like every 25 feet in X and a Y direction, just taking and determining elevations, you're missing data if you do that. So most people use a controlling point where you're using center lines of swales, back of curbs, those kind of things. You're getting that information, and then you're incorporating that into somewhat of a grid pattern. But that's a different story. So once we get this is going to be useful for any type of terrain analysis, and you can do all kinds of studies with this. We can look at aspect, we can look at slope, we can look at water drop, all kinds of things once we get into that. So you have to have a way to properly represent your z-value for each x and y location, or in terms of a z-value, we can also think of elevation. So that DTM has that capability in the software. It's built into it very readily. So there's a couple different terminologies that are used. A lot of people wouldn't use this term, but we either really truly think of what we call a 2.5 dimensional model or a true 3D model. So in what they're defining as what's called a 2.5D model, it's just a terrain model that allows a single z-value to be assigned for each xy location. But if you have a house location at that point, you could have an elevation at the ground level where the foundation is, but you could also have another point elevation at the, let's say, the top of the roof. So that would be what we're calling a true 3-dimensional, so that same XY location can have multiple Z values. So that's kind of unique to a lot of programs. So we have that fully 3-dimensional model where we have multiple Z values. So this is a nice little diagram. This is in your book, and this is showing you that concept in comparison from truly 2D. So we're seeing just the footprint, if you will, of the building in the drawing to the left, and right in the middle, we're seeing, okay, now we've included Z values for each point along that footprint or whatever you're looking at. So this is what they're calling a 2.5D because it only has one Z value representation. But you notice on the other picture there to the right, that's a true 3D because you get a Z1, a Z2, and a Z3 for each XY location within it. So a lot of people don't make that distinction, but that is a true distinction that can be made. So when we talk about the concept of DTMs, that's just a general catch-all kind of name that's saying, okay, I'm portraying this digital model 3-dimensionally some way. But there's different ways of creating DTMs. So we have the primary two sources are what we call the 10 triangulated network, or what's called a DEM, a digital elevation model. So you kind of have those two, and kind of we can use them both actually in a lot of softwares. I would say most of you guys are probably used to the triangulated irregular network. That is absolutely the most common type. In fact, I don't know of any engineering softwares that use any other one than this primarily. So this allows you to create a terrain model where you have non-equally spaced elevations, and what you do is generate triangles through points. So everything is held as an area, and all areas are confined to triangles. Okay, so with this type of methodology, you don't have quadrilaterals or anything else. The shape that you're dealing with is a triangle, and we try to keep the triangles as equilateral as possible. That usually gives you the best type of picture, but that's not always possible. So the points are joined by these non-overlapping triangles. So they have to be triangles. They can't overlap, and they touch edge to edge. This is a very compact method. It's very efficient. And I feel personally, I've used it so long that it's very accurate if you know what you're doing with it. But one of the big things to creating a proper 10 is what we call break lines. Does everybody know what we're talking about by break lines, or fault lines are also referred to?
I do.
Yes,
Yeah.
I do.
You know that if you just take a bunch of points, raw points, and you dump them into, like, say, a program like Civil 3D, you're going to get a 10 out of it, but it won't necessarily be right until you add or incorporate into that your break lines and break line files. Because the triangulation process, it just finds the points and it just starts generating triangles. So the fault lines or break lines give it guidance into how it's going to model. And that's one thing.
One of the guys at our one of the draftsmen at our work made the point to me multiple times that you don't necessarily need the break lines; they just orient the triangles in the proper fashion.
Yeah.
Because he'll draw smaller sites without any break lines in them.
As long as you don't have a lot of change in topography.
Right. It starts to be complete pain. Yeah.
Because what will happen, and you're going to get what I think, Ben, you're going to get like 80% of it will be correct, but 20% of it can be off. And what those break lines do is they give it complete guidance. And if a triangle face shoots across a creek, what you're basically doing is putting a dam in there where there really isn't one. So that's why those kind of things are important. And especially if you have a lot of man-made features like curbs and centers of roads and those kind of things, you obviously need that. So
right.
But yeah, I mean, I agree. You can go in there and you can just dump those points in. You've probably got a pretty good model with maybe 80%. But then, yeah, you got to incorporate.
All I was getting at is, yeah, you can go in and manually flip them all so they line up with your break lines.
Yeah, absolutely, absolutely. And that's, of course, you get into the editing. You can do what's called flip a face. Or swap it. Sometimes it's called swapping. You can also add lines and delete triangles. You guys know that. You can also, one of the things, I'm sure you guys have all experienced this, is where you'll get one blown point where somebody like maybe raised the rod for one shot and then they forgot to do it in the data collector, change it back to the normal setting. So you got one or two shots that are higher or lower than they should be based on that. So you'll get what I call an island or a hole that develops. So you can go in and either fix that point if you know what the change was, or you can just zip the point out so it recontours or recalculates. So yeah, there's a lot of great tools that are available in any of our software to do that. And are a lot of you guys out there that are still doing this kind of thing where you're using data collectors and all that? You guys can draw your break lines while you're out there, right? You guys are doing that?
We do a lot of line work coding in the collector. So
yeah.
As soon as you import it, it's a break line. Your curve line is an elevated break line. Center line is an elevated break line. The whole deal. It is necessary at this point to put out the production we are. Otherwise, we'd be screwed.
Yeah, I absolutely think that the guys on the field should be the ones that are doing it anyway, not a guy in the office that's never set foot out there.
Right, because they've got no idea that that's a ditch line, or you wouldn't know looking at
exactly
points what it really is.
Exactly. And the beauty is that if you can do that out in the field in your data collector, when you download you get your downloads on your break lines as well. So it's what they call field to finish now, kind of. So which is pretty cool. So great.
It makes a huge difference, yeah.
Yeah. Oh yeah. Yeah. Absolutely. Absolutely. In terms of not only in terms of precision and whatnot, but in terms of time as well, because if that gets downloaded, then you've got your model essentially right there. So
it improves the quality and the speed of drafting.
Absolutely. Yep. Absolutely. So the TINS, the triangulated irregular network, is used extensively in engineering software. So like I said, I don't know too many that don't use this method, and probably all of them incorporate all of it. And then even like the ArcGIS stuff and that and whatnot, they use that as well. So let's see. I think I went the wrong way. Hold on a minute. Yeah, so this is actually a picture out of the tin that was been created, and I'm not sure the source of this. I think this says it was ESRI, so this is probably in ArcGIS or ArcMap software. You can really see the triangles here, and I call this the crumpled tin foil kind of view. It's kind of what it reminds me of. And this has what's called color banding applied to it, so you can range your colors out to represent certain elevations, which is also an awesome tool when you get into this. So now this would be the kind of tin. This tin is pretty jagged. You can see those triangles are pretty big. So this would be the kind of tin you might be able to get from Google, Google Earth, Google Maps, but those are not going to be like really good for engineering purposes. But for simple visualization, like I said, or some exploratory purposes, those could be good stuff. So the other type of digital terrain that you can create is using what's called a DEM, digital elevation model. So this type of data is basically just gridded data. So it doesn't have the incorporation of grid lines in it, and it's not random. So with our triangles, we can stratify that. We can space those triangles where we need to. But with this process, you basically are just generating a grid at a certain equally spaced value, and each value then has an elevation. So it's a quick way of doing things, and a lot of remote sensing types of things do it this way, but it's not the way we do it with boots on the ground typically. So this can then be converted to raster grid representation, and you can actually use DEM information in like Civil 3D. So instead of incorporating just points, you can incorporate this information as well. So you could add it if you wanted to. So each grid cell represents an elevation, and we talked about that quite a bit when we talked about the raster GIS. That's more commonly the concept that you see this in. Now the resolution, of course, is dependent on the grid size, the cell size. So the smaller the number, like a 30-meter resolution, the better the resolution, as opposed to like say a 50-meter resolution or a 5-meter resolution. You get better and better data. But again, the one thing about this, you do not have that representation of break lines in this type of data. It knows nothing about that. So you're not going to get a great picture, you know, in my opinion. It's going to just be so-so. So again, 30-meter equals a 30-meter grid size. So USGS has DEM information available, and it's created from digital line graph information. So digital line graph, I think we talked about that back in a couple chapters ago. That's digital information where basically they took the contour lines and scanned those in, and then basically laid a grid over top of it and generated or extrapolated the points to create these DEMs. So you have different levels of information that you can generate to or from. You can also, by the way, most of you guys have probably done this, but you can take contour map data, contours that have elevation on them, and dump them into a program like Civil 3D and generate a tin from that. That actually does pretty good data, but again, even that data does not have break line data. That you can add it, but it doesn't have it per se. Okay, so one of the other types of DEMs would be these DEMs that have covered large swaths of ground on the Earth. So these would be like remote sensing types of things. So one that was created way back in 2000s was early part was what's called the Shuttle Radar Topography Mission. And this was actually pretty neat because this basically mapped the entire Earth. So they generated a DEM of the entire Earth. So it's not going to be great, but it's going to be, they've got data of a whole thing. This was flown in the 2000 Space Shuttle Endeavour mission. And they used a radar to map that. So it was kind of a, you know, kind of like the LiDAR kind of concept. Instead of using light, they used sound. Highly accurate DEM. But again, it's not going to, when you say highly accurate, it's highly accurate to the point, but it's not going to have any kind of break line information. And it captured and modeled 80% of the Earth. So that's, we had pretty much a full view of the Earth as a DEM model. And 30-meter resolution. So think about that. You know, the shuttle was up there pretty high, and they were generating 30-meter resolution. So that's actually pretty incredible. Then 90-meter resolution is available for other areas. So within the United States, we had 30-meter, and then the rest was 90-meter. Additional remote sensing methods have come about. This is the big thing that we see now a lot now is the LiDAR, the light detecting and ranging. And this has really taken things by storm, where you're basically using a laser that fires actually several different wavelengths. It can simultaneously, and it generates a highly accurate DEM, and they're quick as well. So the beams pulse 2,000 to 5,000 times per second. They may even have pushed that rate by now. So this is a active type of remote sensing, because it's actually pushing energy down to the ground and then it's bouncing back and coming back into the sensor. So that reflected light is used to determine elevation. And it's also targeted with or connected to GPS and IMUs, inertial measurement units. So you're getting, with each, as the pulses are going, you're getting GPS information that's giving it a bit, essentially an XY value, and then altimeters, and then you also have the measurements of the IMU information. So it's all really comprehensive, very good data. It's going to provide a really highly accurate data set, XYZ coordinates. And in fact, primarily this stuff was used in airplanes, but now they're miniaturizing LiDAR quite a bit now, and so the drones are now capable of carrying these things now. And you can get 15 centimeter vertical accuracy. They may have pushed that now actually even more. So anybody using LiDAR right now? Anybody using LiDAR data from anybody or any sources?
Yeah, I haven't. We did some stuff in the photogrammetry class with the drone photogrammetry stuff. But
Have you ever used commercial stuff that you used for work at all, though?
no, not for work though.
You guys may or may not be aware of this, but the state of Ohio, a group called OGRIP, you can get 2-meter resolution LiDAR data for free from those guys, which is actually pretty cool. So you just go in and get the data set that you want, and you can bring that stuff into like Civil 3D, generate contour maps out of it. It's pretty awesome. And it's so you might want to check that out if you've never done that. Again, it's not engineering quality data, but it's good for generating nice maps to just get in there, just get a location. But the state of Ohio does that. I think they fly. I'm not sure how often they fly it, but again, the information is completely free. So this is an example of showing you how that works, where you got the LiDAR unit in the belly of the plane, flies over, and it scans it, kind of like we talked about with the satellites. And again, like I said, now your rotor type drones, they miniaturize a lot of these LiDAR units, so they're able to now start to incorporate that. We're seeing that happening pretty readily. This is an example of the LiDAR. This is actually Mount St. Helens in Washington, and that was the one that blew in the 80s. The volcano that pretty much devastated a lot of the sections out there, but that's actually pretty cool. That's a pretty highly accurate map that was generated through LiDAR data. So there's other types of digital elevation model data available. Of course, it depends on the size and the resolution of the area. The USGS, again, distributes a lot of this data. They have an elevation data set, free download, National Elevation Data Set it's called. Gives you digital elevation that covers the entire US, no gaps in the data. That's also awesome because you've got everything right. What you might call a seamless data set, designed to be seamless right there. Same projection and elevation unit, and there's no separate tiles. So in other words, tiles mean like if you have a quadrangle to the east and a quadrangle to the west, those things, there's none of that going on anymore. There's no tiling. Everything is just matched up. And since everything's in the same projection and elevation unit, it just works across the board. So then what you can do is you can just select what section you need to download. You can download that. And then probably in most systems, you would still have a whole lot of data outside of the periphery of where you want to work. So you could actually clip that out much like a cookie cutter and then just incorporate that stuff in. Because if you don't clip that type of data down, it gets to be pretty involved. But like I said, some of you guys, besides this national elevation data set, some of you really might want to investigate OGRIP, because it's really kind of, for one, it's kind of interesting to play with, but it is kind of good to, if you're doing any exploratory types of things on some areas. So you also have the NED data. It's also freely available, the national map, what they call the seamless server. Another online source that you can get from the USGS. And they offer lots of different data sets, including elevation as one of the data components. You just use a specific geographic area, like a latitude and a longitude, kind of clip out the rectangular area that you want to get it from, and it'll take it out for you. So it's available in different resolutions. You have a 1 arcsecond, so that's approximately a 30-meter resolution. And they have a 1/3 arcsecond, which is approximately 10-meter resolution. So that's actually pretty decent data. And a 1/9, which is 3 meter. So like I said, and then the state of Ohio has like 2 meter res. So that's all good stuff. Okay, so many different types of terrain analysis can be done when you have your digital elevation model. So any good geospatial technology software will have these capabilities. Everything we'll talk about here is truly in Civil 3D. They may not call it the same terminology, but it pretty much has that as well. So we have analysis such as viewshed. Now this is one thing that you probably don't have in Civil 3D, but you do have in geographic information system software, the concept of viewshed. We'll talk about that. I think I've mentioned that before. Slope calculation, that's certainly in most engineering software as well as GIS software. Slope aspect, okay, we talked about all of that. So viewshed is allowing you to determine what an observer can see from a particular location on their terrain. And people that use this technology are people that need to see line of sight from point to point. So you might use that like if you're siting towers, let's say for high tension lines, because they need to be able to string those lines from point to point. You can get that kind of information, but primarily a lot of guys that use this are cell tower developers, because they have to have a line of sight between the cell towers and also the users. So they can pinpoint a location where they want to site a cell tower, and then with this technology you can tell it like how high you're going to be above your site. So how high is your tower, 100 feet, whatever, and then it'll do a calculation and it'll show you basically what it can see from that point. You can also see if you've got a lot of areas there where you might call dead zones, where you have hollows or things like that where you can't see line of sight, because radio waves are primarily, they're pretty primarily line of sight, they don't bend. So that's why you get a lot of those dead zones essentially. So what's kind of cool though with this, you can tell it not only the location you're sitting on the terrain, but you can tell it how high above the terrain you're going to be. So slope, of course, we talked about this. Slope is a measurement, rate of elevation change at a location. Actually, if we're looking at, like, say, grid squares, we've already noticed how we talked about how that works, slope on your grids. But on your triangulated irregular network, what you're getting is the slope of the actual triangle itself. So each triangle will generate its own slope value. And essentially that's just a rise over a run kind of thing. And what you can do is then calculate this either in terms of percent grade or angle. Most people would probably use percent grade, but very useful tool when you're looking at siting, like say a subdivision, and you're looking for the, say, the best areas to build housing, for instance. You may want to limit your locations to, say, maybe from 1% to, let's say, 15% is you might consider those your most buildable areas. So what you can do is go in and generate a picture that generates or aggregates all your triangles down into slope, and you can color code that based on, you know, your range that you want to do it. So very, very useful tool. It's also used in hydrologic applications, because, you know, the steeper it is, the faster your runoff is. So that determines that your velocity essentially is your fluid flow. So it also would also determine or allow you to look at accumulation of water in areas as well. We can see that as well. and extraction then of what we call watersheds. So a watershed, I think most of you guys understand what a watershed is, but it allows you to determine the drainage basin area. So each creek that you have is surrounded by basically an area that it's catching the water. And then you get to a ridge, and then the ridge on the other side is going to be into another drainage basin. And all of our software that I've ever used has the ability to go in and calculate watersheds for you. That can then be used as the area that you can do for when you get into hydrologic calculations of pipe sizing and culverts and all that kind of stuff. You need to know how much water is coming into you. So that's determined on the watershed. And there's a watershed 10. Some of you guys may have played with that, but Civil 3D has what's called a watershed 10 surface. So you can go in and generate a watershed based on that. And then that information can then further be fed into your sewer information. Slope aspect, that's determining the direction that your slope is locally facing. And again, that's can also be useful for things we talked about, like energy, those kind of things, calculated as direction, north, south, east, west. Or one of the things I'll do is they have in Civil 3D, they have these things called slope arrows. And what that will do is basically you can generate a little arrow that runs across the face of your triangle. And what it'll show you is the direction the arrow is pointing is the way water would shed, but it would also show you the direction that your aspect is. And you can further color code it. So your arrow can be coded so that, let's say green is going to be a slope between 1% and 5%, and red is going to be a slope between 5% and 10%. So you can not only get aspect, but you can also use it as a slope. That's why they call it slope aspect. And this is, again, used in a variety of applications, energy calculations, environmental applications. You can also look at things like I said, water calculations. So this is a neat picture. This is out of your book, and it's showing you really 3 separate views of an area. And what we're looking at, this actually happens to be from Ohio. This is an area called Laurelville. So if any of you guys have ever been to Hocking Hills or that Hocking region, that's where this actually is. And what we're looking at is just the raw DEM elevations right on the left side. And you can see it's color coded. So the darkest color are the lowest colors. Okay, so it looks like we're looking at a 650 elevation to the highest is 1172. That's where you're getting into your wider areas. You can kind of see those directions of creeks and everything that is developed. And you can kind of see like there's many watersheds that are developed there, and then major watersheds that go together. Now the middle is taking this image and calculating it into a slope of different ranges. So what we're looking at is your greens are your lowest slopes or your flattest slopes. My guess is that's probably in percent grade right there. So that would be from 0 to like 7.6%. And then, so we can range these into whatever values we want. And then we're looking at aspect. So this is showing you the kind of the way that these things are locally facing or locally tilting. And again, that can make a difference in the way water is flowing. So just taking that digital terrain information, you can get the slope information, slope aspect information. Now, this is a digital elevation model information. So this is probably not using, this is probably using the gridded types of information, not the triangular type information. So DTMs are not limited to flat images on the screen of like paper is. Okay, that's the one cool thing. So since your DEMs contain Z values, that allows you to visualize things in 3D views, which is really the neat thing. And terrain visualization, we consider it pseudo 3D. It's not real, obviously, but it sure looks like that when you go into a different view on it. So this allows you to describe a perspective view, a terrain model. So since it's often 2.5D, you're not getting a true 3D, you're just getting like, say, the ground surface. You're not getting all the structures, but for our purposes, actually, we don't want to see all that stuff anyway. We would like to see just what's happening on the surface. So by setting those 3D views up, you can generate that perspective view. And that's just really basically a click of the mouse, essentially, where you can go into a 3D, you can use like a 3D orbit view or something like that in, let's say, AutoCAD. It allows you to get oblique angles that allows you to look at your view in digital three-dimensional appearances. And those points then are elevated in height based on what the Z value of that thing is. So I kind of think of it as you got all your data there and you generate your model, and what you're seeing is you're laying, like, let's say, a sheet on top of it. So you're just kind of looking at your sheet as you see that. And of course, mountain peaks then can be seen jutting up, and low spots, creeks and valleys are going to appear as depressions and other things as you see that. Now, very typically, as you look at that, those pictures, even on hilly topography, look rather flat. So a lot of times what we'll do is we'll go in and exaggerate the Z values just to show greater relief. Usually you have to exaggerate it to show greater. I never do it so much lesser, because usually you always need to see a little bit more, but it does give you a better picture. Not that the data is any better, but it just looks better, that's all. So what you're doing is you're just viewing that point location that's altered, but you're not actually changing the Z value itself. You're just generating an algorithm on how it's going to display it. So a lot of these, the model becomes then interactive, which allows you to do things like flyovers or of your terrain, or like in Civil 3D, you can do drive-throughs. So I always say to students, talk about once you can design a road, you can actually drive down it. And so that's just really incredible to be able to do that kind of stuff. Then of course, your image can be enhanced by actually bringing texture into that, so you can do more realistic rendering. And there's a couple of ways you can do that. One is you can actually bring textures like grass and those kind of things into it. The other way is to actually bring a realistic photo and overlay it. And that's what we refer to as draping. So you can drape a raster image over your digital terrain model. And again, you think of it as just like a sheet that you lay on it, and then that sheet has the printed information, and it stretches the photo or whatever the texture, whatever you're doing to fit on it, like that image of Mount Everest we looked at in the very beginning. So a lot of times you'll take realistic satellite imaging and you can drape it. And I don't know if anybody has ever done that in Civil 3D, but that Civil 3D has a drape routine that you can use. So you can take a raster image and lay it on top of your surface. So scan topographic map, you can lay that over. So here's an example of a scan topographic map as a raster file that has been draped on top of my DTM. And of course it has to match up right, but what it's done is you can see the valley very nicely and you can see the hillsides very nicely. And of course this has contours on it. So it's showing you that. And that's a really cool methodology. You could do this kind of stuff in Civil 3D actually. So DTM, remember, it can be either a grid of elevations, but it can also be triangles. But it can be displayed with color ramping to show elevation change. We usually call that elevation ranging. And you can also then use the things we talked about to make them look more realistic. I use color banding quite a bit, because when I analyze any DTM that I've created, one of the first things I'll do is I will color band it and then go out and look at that in 3D space, like we were just talking about, because any things like high spots or low spots that shouldn't be there, they're going to show up pretty readily, especially if you've been out on the site and you know what you're looking at, or just something that a blown point, it's going to show up real directly by doing that. So another thing you can talk about when we talk about realisticness is this concept of hill shading, which would show you, like, on a sunny day where you're going to get shading and non-shading based on things like time of day and also location within the earth. So what your latitude and longitude is, image draping like we just talked about, and then the concept of vertical exaggeration. So these kind of three things we've already alluded to, but again, we'll just talk about them in depth here. So hill shading is the concept of looking at a shaded relief map that you would see what's happening based on the sun and its position in the sky relative to the landscape, relative to the time of day, and relative to your location. Also the season, so that'll change, like right now our sun's really low in the sky, but as we approach the solstice, it's going to get to its lowest point, which will be in about 20 days from now, and then it'll start to get higher back out. So that again makes a difference. So this allows you to determine where the sun is with respect to the terrain, and again, it's going to be simulating shadows that are going to be cast by that. So governed by primarily two parameters: your sun's altitude, which again, that's season and the time of day, and then the sun's azimuth. So the altitude, you can set values in there between 0 and 90 degrees to control this kind of stuff. 0 is directly on the horizon, to 0 to 90 directly overhead. Sun azimuth, anywhere from 0 to 360 can help you do that. And actually programs, I don't know if anybody's used some BIM programs. You can create some site work in there and you can do this kind of thing that will allow you to do that. So if you've generated a building and placed it on a site, Revit will allow you to do this. It has hill shading capabilities. Okay, so this is showing you your DEM model. I think this happens to be, actually, this is a map from Ohio too. This guy's an Ohio author, so he uses a lot of Ohio data. This happens to be Columbiana County, which is northeastern Ohio, and it's actually a pretty hilly area, as you can see. But we're looking at hill shading of a DEM using different values. So your azimuth and your altitude settings simulate your landscape different times of day. Now, it's not going to work for features like roads and land cover too much, rivers and streams. So another thing that you can do is to make things more visible is that process of image draping, as we just talked about, where you take some kind of either realistic image or other textural type of image, and you basically drape that to match that. So what it's going to tend to do is it's going to stretch it, because if you think about an image that's a rectangle, it has to drape over that jagged surface. So it'll stretch it in certain areas. So the algorithm goes in and takes that and it'll stretch it and then reduce it. But it's a commonly used technique using remote sense data. And like I said, actually Civil 3D has a drape option in it. Anybody ever used the drape option in Civil 3D by any chance that's using it?
No.
Yeah, check it out. It's under the DTM sections, on your surface stuff, but it's there. But it allows you to do that. So here's an example. Again, this is showing you a region. This also happens to be that same map of the Hocking County area. And the left is your just normal DEM, and the right is a digital terrain model that has a drape image on it. So you can see looks like they've draped a USGS map on it. And they've also done hill shading on it. So they've set the sun at 45 degrees and an azimuth of 315 degrees. So besides just the hill shading, we're looking at the drape image as well. And here's another example of a drape image. This is Glacier National Park out in Montana, which has got some of the most jagged areas of the Rockies, very beautiful section. And you can see that was a satellite type image that has been placed on it. And of course it does, it stretches the image to make it, but it fits it pretty well. And this is in Google Earth, so you're just using the Google triangulated irregular network. Now they do use a triangulated irregular network in their data. Okay, so besides hill shading and draping, you can do vertical exaggeration, which basically artificially enhances that Z value. So you're not really changing the Z value, and a lot of times it's not like you're just multiplying it by a factor. So you're not saying, oh, I want to enhance the Z values by, let's say, 2 times. There is usually an algorithm, and it usually has to do with a base level elevation and whatnot. So it doesn't necessarily do every Z value by the same amount, because you want it to look still natural. And if you do it like a common multiplier. It doesn't always give you the exact kind of look to it. But I always find that I'm going to take whatever my z-value, whatever my image is, I'm going to always do as some kind of enhancement to it. It usually gives me a better picture. But the thing to note is that your horizontal scale doesn't change, but you're just altering the z-value look. So you get a vertical exaggeration. They're saying it's kind of multiplied by a common scale factor, and that might be true in some softwares, but I think it's not true really across the board. It's kind of a scaled value based on where you are within that site. So what that does, though, it does allow you to get values such that your valleys are going to appear deeper, mountains are going to appear higher. And of course, this is only going to be used for visualization purposes. But keep in mind, that's all it is anyway, because in like Civil 3D software, you're actually not altering the 3D terrain model at all. You're just actually altering the visualization process of it. So what we're seeing is this is a sequence of images where they're showing you exaggeration factors. Now again, that doesn't necessarily mean 2 times, but what we're seeing is that's what it would look like under normal circumstances. Actually, it's not too bad, but if you want to give it a little bit more enhancement, there's a 2 factor, a 5 factor, and then a 10 factor, which really makes it hugely different. I found though a lot goes a long way. All right, so any questions anybody has? That's kind of this crux of this chapter. Go ahead and turn off the, I'm going to